Okay, so the plan is this. First of all, a very brief introduction in which I will just explain what is the problem we want to solve, okay, and our strategy, okay, so the plan. Then I will introduce TND-PQ, which is a system that we have already developed. It is an ugly name, I know, but it has a reason. That we have already developed for another publication, for an article that is already submitted, and it is essentially a natural deduction probabilistic system. It is nothing so new, but it is quite, it is quite useful for dealing with machine learning systems and this kind of stuff, especially when you want to investigate their behavior from the outside, okay? Then I will define the first notion of fairness that we will consider, so individual fairness. This is to some extent a quite oversimplified notion of fairness, but nonetheless it leads to some troubles, okay, although it is quite oversimplified. In order to deal with these troubles, I will add the causal relations to TND-PQ, okay? We will see that with this move it is possible to solve some issues, but we have also new problems, essentially, especially connected with counterfactual fairness. Now, with counterfactual fairness, you will see that we still have a problem of how to define reality-risk probability is in TND-PQ, okay? And then, of course, I will just conclude. Now, the problem, what is the problem? The problem essentially is that machine learning systems reproduce the behavior extrapolated from dataset, essentially, okay? And from datasets, you can only extrapolate correlations, so statistical correlations. But we know, of course, that correlation is not causation, okay? So this is, a standard assumption in any kind of statistical textbook and also in philosophy of science, of course. So the problem is that machine learning systems, ignoring this distinction between correlation and causation, can have some bias, okay? And indeed, they can even amplify these biases, okay? Let's consider a standard example of bias, okay? Now, a lot of examples come from USA literature. It is quite obvious, but they can be generalized quite obviously. Now, crime rates. Some ethnic groups are more likely to be checked during routine police controls, okay? Just because they are more likely to live in suburbs with high crime rates, okay? As a consequence, they are more likely to be arrested and found guilty of some infractions. This is a standard example, okay? An ML system could learn, and this is not a counterfactual example, it has happened in the quite recent history, from this data that ethnicity is the cause of high crime rates, okay? While, of course, we know that the real story is more complex. We can disagree, of course, in what is the real story behind the high crime rates, but I think that we can agree that the story is much more complex than just this correlation. As an example, usual explanation is that ethnicity is connected with intergenerational poverty and marginalization, which are causally related to crimes and arrest. So this is also relevant when you want to decide in which way you should act in the society, of course. So what is our strategy? Essentially, our strategy is just to use a natural deduction system to describe from the outside a possibly opaque ML system, okay? So this is not the logic for dealing with the actual process inside of machine learning system, but just to describe its behavior. This has some good points and some bad points. Of course, the bad points is that you cannot look at what is happening inside of the machine learning systems. But the good point is that this system can be applied to possibly opaque system, closed source, so in which you do not have access to the program. Now, the simplest approach possible in this case is to define fairness in two ways. Fairness through unawareness and individual fairness. These are standard concepts in the literature today, and we will see the definitions, of course. And we have a definition of individual fairness that is not entirely standard, but that can be generalized. We will prove that our results generalize to the most general and common notion of individual fairness. Then we have the problem of intersectionality. We will explain what this means from the statistical point of view and reasoning. We will treat intersectionality together with monotonicity. In order to treat intersectionality, we will have to complement TNDPQ with causal graphs. Okay, so we have to complement the usage of statistical data with causal graphs. So we will briefly explain what the causal graph is. I don't know if you are already aware of this topic. Okay, of course, if I say something that is too obscure, just stop me. You can make question when you want. And on the contrary, if I just say things that are too obvious, you can just tell me to move forward. So after having added causal graphs, we will look at intersectionality again, and we will see that it is possible to give a solution, a formal solution to this problem, but we will have a more deep problem with counterfactual fairness. So first of all, TNDPQ. Now, this is a little an intimidating system, but it is quite obvious, okay? It is just that the syntax is a little strange, okay? It is just a natural deduction system for probabilistic logic, okay? We have, first of all, the syntax, okay? That is all the complex part is the syntax here. Okay, we have atomic terms, okay? A, B, C, possibly with numbers, and we have terms that are defined more or less as usual, okay? So we have pairs, and we have also the possibility of a conditional, okay? And we have the output. So the idea is that a term has an output, or this is the standard terminology in computer science. From the point of view of statistics, we have variables that receive values, okay? And we have atomic values or atomic outputs, and we can compose the outputs, okay? We have negation and disjunction, okay? And we can also have conjunction and implication. Now, the definition is a little complex. We will see why. Just because, of course, an atomic term, okay, can have, we will see it in the next slide, also non-atomic output, can have negative or disjunctive output, but it cannot have conjunction. So it is a little strange, but it is something standard in all type system, essentially. An example, okay, of atomic terms. AN are atomic terms for attributes, essentially. We use them for attributes or features, such as gender. General terms, we use the terms T, U, U, okay, are used for any kind of composition of atomic terms, like in this case, pair, age, gender, okay. Atomic outputs are stuff like female, okay. Outputs in general are something like male or female, okay. Probabilistic outputs are stuff like, I don't know if you can see this, less than 20 years old for the age, and the female with a probability of 0.25, okay. And there is a reason why we have conjunction and implication together also with negation and disjunction only for probabilistic outputs. The reason is the following. we define values attribution as an atomic term that receives an output. Okay, so here we can have also disjunction and negation. Okay, but not conjunction. And we have probabilistic values attribution, in which we have terms that receive probabilistic outputs. Okay, we will make some example to make this a little more clear. Then we have lists of values attributions that are just what they sound like. They are just lists of this kind of stuff. Okay, as an example, this is a standard value attribution. Okay, and an example is this. Okay, gender receives male or female. Okay, this kind of stuff will be used in the left-hand side to give to the system the information that we know. Okay, this instead is a probabilistic value attribution. Okay, and the example is this: age, gender, less than 20 years old, and female, with a probability 0.6. Now the probability only occurs on the right-hand side. So the idea is that you have a system in which you give all the information you want, all the information you have about a point in the data set, and you ask for a prediction about a specific term that will be the target term and a specific output. Okay. List of values attribution are just this kind of objects. Okay, so it is just a list of this. So, and a list of values attribution will be used to give essentially to the system all the information you have. So the judgments are just this. We have a list of values attributions. Okay, so all the information you know about the data point, and on the right-hand side, the probabilistic value attribution. So what's the system, the decision of the system about the target variable. Okay, as an example, you could give to a system all the information you know about the person, okay, and ask for a decision. Okay, what is the probability that this person will give back the loan that he or she have received? Okay, so for this reason, here we have a probability, but we do not have probabilities on the left-hand side. Now, this is just atomic judgment. For some reasons, it is better to distinguish between judgments in general and atomic judgments. Okay. And an atomic judgment is just what changes is on the right-hand side is just when you have a decision about an atomic term and an atomic output. Just this. So this is the standard form of the judgment, and the sigma, small sigma, specify what we know of the subject, and F is the probability that the term T receives the value beta for, of course, the subject sigma. Okay. Now the rules are quite simple. They could seem a little intimidating, but they are very simple. The idea of the atomic query is just that we assume that we know the behavior of the system about atomic terms and atomic outputs. Okay. And the system, what it does is just to make the prediction or the decision of the system coherent with the logical structure of the query. So, as an example, we can know that the system gives some kind of output about some atomic properties, and we can wonder what it does when we ask more logically complex questions. And we can add logical complexity both on the right-hand side, and we can do this for, as an example, with conjunction, okay, or on the left-hand side, as we will see. Now, this is standard probabilistic logic. This kind of maybe could seem strange structure of the introduction of conjunction is just due to the fact that probabilistically, to have the probability of A and B, you need to use the probability of A and the probability of B given A. Okay, so this works more or less like conditional probability. Okay. The elimination rules, of course, can be derived by the introduction rules in a quite uniform way. Now, we have seen that on the left-hand side, we only have atomic terms, okay? And conjunctions do not apply to atomic terms, okay? But this junction does, and indeed for this junction we have both right-hand introductions and left-hand introduction. Indeed, here we have a disjunction on the left, okay, while we here introduce a disjunction on the right, okay. But the intuition behind this is just the same that I've already given, essentially, okay. So we just compose from the logical point of view the output of the system logically, starting from the atoms and making much more complex, logically complex outputs. Okay. The same can be done, of course, for negation. Also, negation has both a right-hand rule and the left rule. That's this one. Okay. So this was the system we have developed. In the previous work, we have just proved that essentially we have wondered whether some results about trustworthiness were preserved when we compose machine learning systems, when we copy machine learning system, and when we note that the system is not completely trustworthy, okay, we were wondering whether this incomplete trustworthiness is preserved when you ask for more logically complex questions. Okay, so this was the previous work. Here, instead, we want to deal with fairness. Now, first of all, which kind of fairness? The easiest approach possible to fairness is just a fairness through unawareness. Okay, I think this is the kind of fairness everyone has in mind when think about algorithmic fairness. An algorithm is fair through unawareness so long as any protected attributes, so these are the attributes you do not want to be used in the decision, I don't know, maybe gender, sexual orientation, of course, ethnicity and this kind of stuff, okay, are not explicitly used in the decision-making process. So essentially you have a machine that is blind at this data. The machine does not look at this data for the decision, so you know that it is fair, okay? Now, it has some problem, this definition. It is quite obvious, it is, I mean, it is the first definition that anyone looks at. It has some problem. First of all, fairness through unawareness cannot be checked from the outside because we do not know what the machine look at. Okay, if you just look at the behavior, you have to use a less, we should say maybe an extensional definition of fairness. So individual fairness, we claim this, is a way of checking fairness through unawareness for opaque systems using what are usually called post-hoc methods, okay? And this is the definition of individual fairness. An algorithm is individually fair if it gives the same outputs to data points differing only for one protected feature. So instead of looking at what the machine learning system uses, you just look at what it gives, okay, at the output, okay? And it seems similar, okay, but it is just purely behavioristic, if you want. And the idea is essentially this, okay? In our system, individual fairness can be defined as a rule in this way. We have the same outputs because the frequencies are the same, okay? Of course, we are dealing with the same target variable, okay? And we are changing the value of the protected attributes. And we have that the system is individually fair regarding protected attribute A and target variable U. Of course, vice versa, the elimination rules just give them. If you know that the system is fair and you know the frequencies, when you have the value for the protected attribute, you can know that you just know that the frequency of the output is the same when you change the value of the protected attribute. It's something quite normal, I would say, right? Now, this can be seen as some kind of weakening, essentially, because what you have when you have individual fairness is that if you make a decision without giving the information about the protected attribute, then you can weaken adding information about the protected attribute and nothing changes, okay? So for this reason, we say that the system is not monotonic, but when you have this property of monotonicity, so weakening essentially, the system is individually fair, okay? Now, what is the problem of intersectionality? The question is this. A system that is fair regarding two protected issues, but taken separately, okay, is necessarily fair also regarding both of them taken together in this way. And now, for fairness through unawareness, we have this property, of course, because if we know that the system does not use one element and does not use the second element, it cannot, of course, use the pair of the elements, okay? Cannot use both of them. But for individual fairness, it could seem strange, but we do not have this property. And I will show you an example, okay? First of all, remember, we characterize the behavior of opaque systems. So we do not know why the system is fair. We just observe that it is fair regarding this property. And the problem is that biases can emerge in the intersection of protected categories. Assume that the system is trained, okay, so it is not fair because it has some protection, so fairness through unawareness. It is fair just because it is trained with this data set, with the following data points satisfying a sigma. So we do not have to wonder about sigma if it holds or not. In all these points, there are 680 points, sigma hold, okay? But we have this situation. We have two protected attributes, A1 and A2, each with two possible outputs, alpha 1,1, alpha 2,1, alpha 1,2, and alpha 2,2, okay? And we assume that the target variable, okay, has also these only two possible outputs, one positive and one negative, okay? Let us consider that this is the probability associated with the positive output, okay? I don't know, we give you the loan, or you are accepted as, I don't know, as a guest in somewhere, okay? We have this situation. We have that regarding attribute 1, the system is fair, okay? Because for both value alpha 1,1 and alpha 2,1, the system is fair. Regarding attribute 2, the system is fair, okay? Because if attribute A2 receives value alpha 1,2, we have this rate of acceptance. And if the attribute A2 receives values alpha 2,2, we have this positive output, okay? But if you look at the intersection, okay, and these are the data points in the data set used to train the system, so the system will look at this intersection for its behavior. We have that as an example when attribute A1 has value alpha 1, 1, and attribute 2 has value alpha 1, 2, we have 0.88 success. But when we change the value of attribute A2 to alpha 2, 2, we have 0.72. And there is no trick here, okay? If you do all the mathematical operation, there is nothing, there is nothing wrong. It is as it should be, okay? I don't know if you find this surprising or obvious, because depending on the people who look at this, find this obvious or surprising. So we have that a system can be fair, but not intersectionally fair. And this is very problematic, especially from the applicative point of view, because if you are a company that wants to market its own software as fair, it just has to gerrymander in some way the fairness, asking for the right property. Maybe the company knows that the data set is not fair regarding some attributes, but you can look at intersection and find some properties that look great, and yes, this system is fair. You have to check for all the properties, otherwise it is quite a weak property. So the system is fair, okay, it can be proved, but it is not fair when you look at A1 and A2 together, okay? Now, I have seen that we use a quite weak notion of individual fairness, okay? There are some possible generalizations well known in the literature. Here we have just two examples, okay, in Kushner and Asher. Now, Kushner defines individual fairness in this way. An algorithm is individually fair if it gives similar predictions to similar individuals. So it is not dealing about identical individuals, just similar individuals. Formally, given a metric, if individuals I and j are similar under this metric, okay, so there is a distance that has to be smaller than something, then their prediction should be similar. Now, it should not be so surprising that this problem of intersectionality generalizes this kind of definition. Okay, now it is a definition of individual fairness that is much more interesting from the formal point of view, because especially here you have to define the good notion of distance, and it will depend on also how you evaluate different possible attributions of values on the left-hand side. But the problem is still there. And why? Because, as Asher says, individual fairness assumes that the features in sigma, he uses in other terms, etc., but in our language, the features in sigma are mutually independent. Okay, and this is the real reason why we cannot have a property of weakening or some condition for weakening. So our proposal is to essentially add causal relations to the system and use some kind of labeled calculi, okay, so to say. Now, what is a causal relation? First of all, okay, an event, I will use sometimes this term in statistics, just defined as a variable receiving a value. Okay, so it is just this, okay? And A1 is a direct cause of A2 if the value of A1 is used in the function that calculates A2. So there is this interpretation, but I think that the notion of direct cause is quite obvious, okay? This is what you think about, okay? Is this, I would say, intuitive notion of causality. Of course, cause in general is just a closure under transitivity of direct cause. Now, a causal graph just tries to capture the intuition about causality using graphs, okay? We have nodes that are events, okay? Sometimes I will just write the variable or the term in the circle, in the node, okay? It is, but of course it is not just the variable, it's the variable receiving a value, okay? And direct edges are direct causal relations. Okay, so in this case, this is the direct cause of this is the direct cause of this, and this adds also this one as a direct cause. Okay. Now we will use causal graphs to decide for conditional independence, because conditional independence is what we need to have weakening. A1 and A2 are independent, conditional on A2 if this happens, okay? So if the probability of A1 receiving a value when A2 has this value and A3 has this value, so conditionalized on these two, is the same as the probability of A1 receiving the same value when you conditionalize only on A3. So adding this one makes absolutely no change in the probability, okay? And for this reason, we say that this one and this one are independent, okay? This is what we should have if we want weakening to hold. So the purely statistical way of deciding weakening uses just conditional independence, investigating in conditional independence with a brute force mechanism. Okay, you look at the tables and you can have plenty of data and you can rely only on the data and you have to check whether you have conditional independence. But we can use causal graphs to correct and predict conditional independence. Correct because we can decide that some conditional dependencies are just not causal dependencies, like in the example I've used at the beginning, okay, correlation between ethnicity and crime rates. And the idea is just this. First of all, we define some condition of independence for the easiest connection possible in causal graphs. This is all literature, okay? It is not something new we are doing. You will see in the bibliography, of course. The easiest case is always the connection of three nodes, and we have three kinds of connection: collider, chains, and forks. But essentially, we could also distinguish them in colliders and non-colliders, because forks and chains more or less behave similarly. Now we have that X and Y. So let's say the father and the mother of this of the son of the single son are dependent, conditional on zeta, but independent otherwise. Okay. Standard example is when the result of a coin. Okay. Consider X when you throw a coin. Okay, the result can be, let's say, 1 or 2. Okay. Y, you throw a coin 1 or 2. Here we have the sum. Okay, this is independent from this because just 2 coins. Okay, they become dependent if you conditionalize on the sum, because if you know that the sum is 3, as an example, well, the fact that this makes 1 is not independent from the fact that this makes 2. Okay, you can derive that if this is 3 and this is 1, this has to be 2. Okay, a more significant example from our point of view is this one. Okay, we have, this is just a toy example, of course. We have the ethnicity and the sentence of a person found guilty of some crime are mutually independent. Okay, but still we have that they are connected with recidivism. Okay, the result is that ethnicity and sentence are causally relevant for deciding recidivism. Okay, so an ML system that uses recidivism to decide the sentence is necessarily biased. Why? Because if you put recidivism on your left-hand side and your conditions, then this and this are correlated. Okay. Another example is fork. We have age, okay, and marital status and salary, okay. So still x, y, and zeta. Y and zeta are dependent, of course, okay. Standard example here is you have fire, you have smoke, and you have heat, okay. But independent conditional on x, okay. So if you look at, if you see smoke, you assume, okay, there should be a fire, and if there is fire, there will be high temperature, okay. But if you already know that there is fire, the fact that you see smoke gives you no information. So for this reason, they become independent. An example about my computer science is the following: a machine learning system deciding about laws. Okay, let's say that it wants to be fair regarding marital status, just because it is not a good idea to ask someone to get married just to have a loan. Okay, it is not something you usually considered. If it uses age as a parameter, then this is only a toy example, of course, because the real causal graph is much more complex. But in this situation, salary and marital status becomes mutually independent. Okay, and this is something good. Okay, if you want to be fair in this case. So depending on where you conditionalize, you have fairness or unfairness. I think I have 10 minutes more or less.
I would say 24.
Okay, yeah.
Because we started 16.
Okay. So I will also do the chain. Okay. Now chain, and we will see that it is similar. We have still x, y, and z. This is standard chain.
Yes, including the Q&A.
Including the Q. Okay, including the Q&A. So okay. Maybe I will skip chain. Okay. Okay. So what is the idea about TNDPQ? But the basic idea is just to put causal relations in TNDPQ. How can we do this? The idea, but this is just an early stage of the work, of course, is to add immediate causal relations with this triangle, and then the connection, let's say, with this diamond. Okay, and this just means that AJ is an effect of AI. This means that AI is connected to AJ with a path that has some nodes that are non-collider, M, and in some set of nodes that are colliders. So we have to distinguish between colliders and non-colliders. So we add some assumptions about the causal structure that we think should represent the topic we are dealing with, okay? And we have an automatic way of calculating the connections, okay? So an example, the chain, we didn't explain it. Let's say the fork, okay? We have this situation, okay? So we have AJ and okay? So this is the fork. And we just add this correlation with point I, that is the connection, essentially, okay, on top. And the same, of course, for the collider. Now, we also have to deal with transitivity, because, of course, with this rule, we just obtain the easiest fork possible, with just one point in the middle, the easiest chain possible, and the easiest collider possible. But we have to deal with the path in general between one node and another. So we need to have transitivity. Now, transitivity is a little tricky, because the standard connection between the nodes in the causal graph has 3 elements. So it is not so clear how you will have transitivity between connection, because you can be in this situation in which you have just one node in common, or you can be in this situation in which you have more than one node in common, okay? 2 nodes especially. When you have more than one node in common, okay, so we have the situation on top, it is much easier. You just have the rule of transitivity, and you can just have a union of the data point or the nodes. Okay, when you have that they just touch each other, the two parts in one point, then it is much more complicated because you have to look at how they are connected. Okay, so you need to consider also the causal relations in the connection. Okay, this is not something so strange, but this is a little trick in the details, and so the rule is a little tricky. But I mean, it should work. Okay. And of course, we have it depends on how it is connected. It can be connected by a chain and fork of the collider. So it should be chain transitivity, fork transitivity, and collider transitivity. With this, we can have a criterion for weakening. Okay, the idea is just this: we have the judgment. Okay, we want to weaken, and we have a set of assumptions about the causal relations. We first of all use all the applicable rules for the diamond, okay? We have all the connections. And then we can apply weakening by considering these conditions, okay? Of course, we are using, this is the target variable, and this is the variable used for the weakening, okay? We have that there should not be a direct causal relation between them, and a much more complex condition to regard the paths. Okay? For all connection between AJ and T, so this one and this one, for all, because we just look at all of them if they occur here in the derived assumptions about the correlations. Okay, then we can have two possibilities. We can have that the intersection between the non-collider nodes and all the terms that you have in sigma are different from zero. So you conditionalize those on at least one non-collider. So you conditionalize on at least one fork or one chain, or you do not conditionalize on all the colliders. Okay, and this for each possible path between these two. We will see an example. Okay, that makes it a little maybe clearer. Okay, let us consider this causal graph. Okay, and assume that this is the target variable, okay, A4. I just put 4, but this is A4, okay? And we are trying to weaken for A1 and A2, okay? Let us consider this one time. Now, A1 and A3 are connected with a non-collider because it is a chain, so we have this situation. And we have sorry, A1 and A4, I think this should be A2, okay, A2. AT and A4 has a collider, are connected with collider, okay? So for transitivity, we have this situation. This should be A2, okay? We have this situation, A1, A4, with this path, okay, are connected with the non-collider 2 and with collider 3. By the other path, we have that A1 and A4 are connected with a collider A5. Okay, so we know that we can weaken if A1 with A1 in this case, if A3 is not in sigma. Okay, so we are not conditionalizing in sigma. A3 is not in the information that we give to the system, okay, to decide. Or A2 belongs to sigma, okay? And in addition to this, because we have to block this other path, we have that A5 can never be in the conditions that we are using for deriving our conclusion, okay? And I think I will skip the other example, it's identical essentially, okay? So intermediate conclusion that maybe should be the conclusion, probably. Okay, without causal relations, we have to prove individual fairness and intersectionality by brute force. But with causal relation, we can use just diamond. It is not so elegant, maybe, but it is already better than using just brute force method. Also consider that the best way of using causal graphs, to be honest, is to move between statistical data and causal graph to correct one with the other, because sometimes you have to look at the causal graph to understand what is going really on from the statistical point of view, and sometimes you want to change the causal graph because you are maybe oversimplifying something. Okay, so I will just say 2 words about counterfactual fairness. So just the problem, okay, without any kind of attempt of solution. What is the problem? What is counterfactual fairness? It is the notion that tries to solve this, to answer this question. Could I be treated in the same way as the expected actually to be different? Now, this seems something like individual fairness. Because if you have mutually independent features, indeed the counterfactual fairness is the same as individual fairness. But if you add causal relation, this makes the notion much more interesting and problematic. Just an example of why counterfactual fairness is different from individual fairness. Consider this example. When you say someone, you have to study more to improve your grades, okay? You have 3 variables, hours of study, knowledge, and grade. If you look at it from the point of view of individual, of mutually independent variables, you will change hours of study without changing knowledge. Of course, to make sense of this statement, if you had studied more, you would have had another grade. You have to consider the causal relation between hours of study and knowledge. For fairness, another example is maybe more useful. Instead of using hours of study, consider school funds. Okay. Of course, you cannot investigate fairness in this field without considering the causal relation between the money given to the school, the kind of school that you have attended, and this connection with knowledge. Okay. But this is very problematic. This asks for some kind of surgery interaction with the causal graph, and we have no idea how to deal with them from the point of view of the system. By the way, this is also needed to solve statistical problems like Simpson's paradox, but I will not go into detail because we don't have time, okay? So just a very brief conclusion, ML systems are purely statistical correlation, use only purely statistical correlations, and this can lead to biases. Fairness protections can be implemented to avoid such biases. Individual fairness defines fairness when all terms in sigma are mutually independent, but we can treat intersectionality only with brute force methods. By using causal relation, we can solve some of the problems. But in this way, counterfactual fairness becomes different from individual fairness. So to be honest, we should have also a solution to this problem. And we still have to find a solution for counterfactual fairness. Okay, thanks.